Okay, so here's a few examples. We'll go through them one by one. And in each case, we're given a set of vectors, and we need to decide if they're linearly independent. So let's start with the first case. We've got one vector here, 3, -2, and another vector here, -6 and 4. And the question is, is it possible to form a linear combination of these two vectors that ends up giving us back and resulting in the zero vector where all the weights aren't zero, or in the sense that at least one of the weights isn't zero? But in this case, you could just play around with it a little bit, and you'll see that it actually can be done. And in particular, it's this. If I take 2 times the first vector, and I add that to 1 times the second vector, well, that'll do it, right? Because what ends up happening is you end up getting the zero vector. And you could check, right? The first coordinate, 2 times 3 will be 6, minus 6 will be 0. Then you have 2 times -2, that's -4, plus 4 will give you 0. So here you have the zero vector written as a linear combination of the two vectors in the set S. And at least one of the weights, in fact, both of the weights are non-zero, but all that matters is at least one of them is non-zero, right? You've got a 2 here and a 1, an invisible 1 in front of the -6, 4. So we've got these are actually called vanishing linear combinations, by the way. Whenever you take a linear combination of any vectors and you end up getting the zero vector back as the result, then that's called a vanishing linear combination. So we've got ourselves a vanishing linear combination where at least one of the weights isn't zero. Therefore, we can say that the set S is, so what's the opposite of linearly independent? It's linearly dependent. Now, we could certainly say that it's not, that we could have said S is not linearly independent. That's also correct, but it's just a little easier to say linearly dependent. It's easier to say something in terms of a property it does have rather than doesn't have, because you don't have the extra word not in it. That has to be added there. Okay, so here's another set of vectors. This set is called K, and we've got two vectors, 1, 0, 0, and 0, 1, 0. So how do we answer in this case? Well, you could start playing around. You could start writing down some linear combinations of the vectors in K and see if it's possible to come up with the zero vector somehow. But in this case, you'd find that no matter what you tried, just wouldn't seem to work. So then you'd probably start to wonder, well, maybe they are linearly independent. So how do you check that rigorously? Like if you're trying to show that they're linearly dependent, it's fairly straightforward. All you need to do is come up with a way to represent the zero vector as a linear combination of vectors in your set where at least one of the coefficients or weights is not zero, right? That's it. You only need one example to justify the conclusion that you want to make. But in this case, if you want to say that this is a linearly independent set, it's not enough to just show that some linear combination with some choice of weights doesn't work to give you the zero vector. What you have to do is you have to show that it is impossible to write the zero vector as a linear combination of these two vectors, no matter what the weights are. So here's the strategy for doing that is you would just do this and say, okay, well, let's suppose we did it. Let's suppose that C1, that'll be our first weight, times the vector 1, 0, 0, plus C2, that'll be our second weight, times the vector 0, 1, 0. Let's suppose that ended up giving us the zero vector somehow. We won't make any other assumptions. And from this line only, I'm going to put a period, that's the end of our assumption. From this point on, we have to be able to prove, just from this assumption, that both C1 and C2 would have to be zero. But the good news is, just follow your nose now. Turn this vector equation into an augmented matrix of a linear system, right? We know how to solve systems like this. They're going to look like this. You're going to have an augmented matrix that looks like this. And guess what? The bottom row is just a row of zeros, so you can ignore it. This is already in reduced row echelon form. You don't even have to do any work to solve this. You can immediately conclude that C1 is equal to 0 and C2 is equal to 0. That's the only solution to this system. So I'll put it therefore because that's our conclusion. So just based on this assumption alone, we were automatically able to conclude that both of the weights are equal to 0. So there we can say now, therefore, K is linearly independent. Okay, so that's an example of how to show a set of vectors is linearly independent. Now, it's not always going to work out quite so nicely. Like, for example, this just almost seemed too good to be true, right? And it really, what it is because these vectors, these are actually, we'll talk more about these in a future section before the end of this chapter. These vectors have names. They're perfect vectors in some sense. They're two of the three standard basis vectors of R3. They point exactly in the directions of the axes, in the positive half of the, they point exactly in the direction of the positive half of the x and y axis in R3. So they're perfect in some sense. So it's not a surprise that things just worked out so nicely. You didn't have to do any row reduction on your augmented matrix, and the solution just sort of fell out. And it just happened to be exactly the solution that we wanted. But sometimes it won't work out quite so nicely. Let's take a look here at this example. We've got a set of 3 vectors now in our set's called T, and we've got 3 vectors here. Okay, so in this case, you know, it's easy to kind of find yourself in a situation where you don't even really know one way or the other. Are these going to be linearly independent? I don't know. And unless you were to draw the vectors or really start playing around and writing down a lot of linear combinations, you may not find yourself leaning in either direction. You might not really have any clue whether this set is linearly independent or not. So what do you do in that case? Well, you can always just do the same thing we did here. Start by pretend you're going to prove that they are linearly independent, and then try to do that. And somewhere along the way, you'll either be successful or you won't. So let's start with that. Let's suppose that we have a linear combination of these 3 vectors. So 1, -2, 3, plus, so C2, 5, 6, -1, plus C3 times the vector 3, 2, 1. And that's going to be equal to the vector 0, 0, 0, the 0 vector. So let's start with that assumption and see where it leads us. Okay, so, well, we're going to write down the augmented matrix of the linear system that corresponds to this vector equation. And that'll be this augmented matrix. Now, as I've done a lot lately, I'm going to fast forward through the row reduction. Okay, if you do the Gauss-Jordan elimination method and carefully do row operations until this is in reduced row echelon form, this is what you'll end up with. So, and then then we'll carry on from here. Okay, so there's a fair amount of work to get here. You have to do several row operations to get to this point, but once you do, now you can extract the general solution. You're going to assign a parameter to C3, and then C1 and C2, those will be basic variables, so you'll write down the equations that correspond to the pivot positions for those variables, and you'll isolate them and plug in the parameter that you assign to C3, which in my case, I would use S usually. So you'd end up with this. You'd end up with -1/2 S, -1/2 S, and then S. And this is true for any real number S, or for arbitrary real numbers S. If anyone is stuck on how I got to this point, because I did skip over some details, you're always, as always, encouraged to come talk to me. I'll be happy to clarify and fill in the details. But from here to here was just row operations, and then from here to here is just our standard procedure for parameterizing a system. Okay, but so we didn't get just the trivial solution here, right? Here in this case, for part B, we started with this assumption. We started by assuming we could write the 0 vector as a linear combination of the 2 vectors in our set, and from that assumption, we immediately got only the trivial solution where both of our weights had to be equal to 0. But in this case, we had many solutions. So at this point, you know that actually that set T is not going to be linearly independent, but we're going to do a little bit better than just say that conclusion now. What we're going to do is, if you want to show that a set of vectors is linearly dependent, you want to come up with a vanishing linear combination, like we did up here, right? Here we had a set of vectors, and we concluded that they were linearly dependent. Well, this is an important part of the puzzle, coming up with an actual linear combination where not all the weights are equal to 0, that gives you the 0 vector. So we're going to do that here. And, well, this tells you how to do it. Just choose the value of s to be whatever you like. And in fact, as long as you choose it to be any non-zero value, it'll work. However, you've got some fractions here. So because of these fractions, it'd be nice to come out with weights that are whole numbers. So what we'll do is we'll take s equal to 2. That way the 2 halves will disappear. I'm going to carry on up here so I can fit this on this page. So take s equal to 2, and that'll get us c1 is equal to -1, c2 is equal to -1, and then c3 will be equal to 2. So in other words, going back to the context that these variables came from when they were first introduced, that tells us that this vector equation will be true if we plug in these values of c1, c2, and c3. So let's do that. So we're going to have -1 times, I'm going to write small so I can fit this in on this line, plus -1 times the vector 5, 6, -1, and then plus 2 times the vector 3, 2, 1. And that gives us the 0 vector. Okay, that follows from the work that we've done. So that's the vanishing linear combination that we're after. And so now we can say, therefore, this set T of vectors is linearly dependent. Okay, so I really want to emphasize the fact here. When we were solving that system, as soon as you get to here even, you're going to recognize that, hey, one of our columns is not a pivot column. We're going to have a free variable here, which means our general solution is going to have at least one parameter, which means we're not going to only have the trivial solution, which is a hallmark of linearly independent vectors. So really, once you get to this stage, or even this stage, you know that the vectors are not going to be linearly independent, so you technically could jump to the conclusion that they're linearly dependent. But actually obtaining a vanishing linear combination where all the weights aren't 0, that's an important part of your conclusion. So you want to go further and you want to actually come up with a linear combination that gives you the 0 vector. Okay, so that's a few examples. We'll take a look at the next page in a moment.